All right, so today we're doing section 3.8, which is solving problems involving exponential growth and decay. There is no calculus today. This is nothing but a review of your algebra. You have done these types of problems before, but maybe not in this, they probably haven't been presented in this way. We're going to talk about them for a few minutes. We're going to review some formulas, and then we're going to walk through the homework problem by problem together. Your numbers will probably be different from my numbers, so you will need a calculator to do your own number crunching while we work through the problems together. All right, now, why are we doing this when there's no calculus? Because there will be calculus that relates to these questions. It doesn't really come up until chapter 9. I don't know why they do this section in chapter 3. I truly don't know. We almost put it with chapter 9, and then we decided, nope, we're going to be faithful to the book, and we're going to put it where it belongs, except then when we had it where it belonged, it pushed the test to today, and obviously, for obvious reasons, we couldn't test today because there's only 10 of you in the room, right? So, yeah, so we had to move it, so we moved this to the end, but we didn't move it far. So anyway, so we're doing section 3.8 today. So, exponential growth and decay. I'm going to just zip through this. So, in natural phenomena, quantities grow or decay at a rate proportional to their size. That's a big deal. You don't have to write, honestly, you don't have to write down anything today. Like, you just have to write down enough to be able to work through the problems. But this is not, you won't be tested on it on the last test. You're not going to be tested on the next test. And we're going to expect that you probably forget most of this by the time we actually get to chapter 9. So anyway, if you want to write down, you can. But the whole point of this is that in natural population growth and decay, populations grow or decay at a rate proportional to their size. So their growth rate is proportional to the actual size of the population at any given time. Now, because of that, you end up with this little formula, because, of course, what's a rate? It would be a derivative. So your f prime is equal to, do you guys know when you say, like, is proportional to, it means equals k times, you have k is a scalar multiple. So if y is proportional to x, that means y equals kx. K is called the constant of proportionality. So it means x is a scalar, or y is a scalar multiple of x, right? It really went both ways, but anyway. So whenever two things are proportional, you have, this is just standard K notation for proportionality in math. So in this case, the rate is proportional to the size of the population, or whatever we're talking about. This is the basis for how you are able to derive a formula to give you population values for any given time. And the formula that you guys are used to seeing for standard population growth and standard radioactive decay, the one that you guys are probably used to seeing is this, right? Okay, we're going to talk about this on the next slide. But just so you know, if you have this function and you solve it, meaning when you learn how to solve a differential equation, if you solve the differential equation, you end up with that. PERT is derived from this concept, knowing that a rate of change is proportional to the amount present. So anyway, that's the whole kind of background that leads into what we're doing. All right, so anyway, so it talks about this is really strictly without other factors influencing, right? So if we're talking about population growth, it's talking about we have an unlimited environment, we have adequate nutrition, we have disease immunity. If we don't have those things, like if there are restrictions, then growth rates are very different. And then we get into what are called logistic functions that end up having populations that are forced to level out because of different environmental factors affecting them. But for now, we're just going to assume there's no environmental factors. It's just going to shoot up to infinity. All right, so also we get radioactive decay follows the same process. First order reaction rates follow the same process. And of course, continuously compounded interest in savings accounts follows the same process. All of these different types of scenarios all follow what I like to call the PERT model, P-E-T-R-T. They all follow the same model, and they're all based on the exact same thing, which is the rate of growth is proportional to the amount present. Okay, again, you don't have to write this down, but what they're saying here, instead of writing f prime equals kf, they're rewriting it in this notation. This is the same thing as f prime equals kf. It's just that instead of f, they're using y. So dy dt equals ky. This is how, like, what you really use to solve the differential equation. And what does it solve to? It solves to this. So you guys used this in calculus. We don't use PERT. We use sect, CE to the KT. It's the exact same formula. But there are reasons that we use the letters C and K instead of P and R. So in calculus, this is going to be the MacDaddy formula we're going to be using today for all of our problems. Okay, before we move forward, quick question. So if my time is 0, if I plug in a 0 for t, what do I get? This is 1, which means my y equals c, right? So what happens is whenever you're at time 0, your amount is c. So what does c represent? C always represents your starting or initial amount. All right? C is always the amount, whenever you're using this model, like not forever and ever, but when you're using this model, C will always represent your initial amount that you start with. Okay. All right. Now, I made a handout of the examples we're doing today, except we're not going to be doing these examples. So the only thing that you need on your paper, and I'll go ahead and give you the handout anyway, even though we're not doing them. But the only thing you need on your paper, you need 2 formulas. You need this, y equals CE to the KT, and you need dp dt equals kp or dy dt equals ky. The dp dt and dy dt, they're the same thing, it's just they're using p for population. But dy dt equals ky is the same thing. Now, if you line them back up, so here we had PERT and we had CE to the KT. So we just said that C represents your starting amount. What does K represent? What is K? What does R represent? What's R stand for? Rate. K is your growth rate, right? Your rate of growth or your rate of decay. So whatever your growth, your rate of growth or rate of decay is, that's K. So in populations, they call it you'll see in your homework, they'll call it the relative growth rate. That's just fancy talk for K. So, in your homework, the most difficult and convoluted problem is the population question. Should we start with that or end with that? End. You want to end with it? How about we do one to kind of break in a little bit, right, kind of get the feel for it. Then, so we'll do a kind of an intro, then we'll do the population, then we'll go back and hit the other two. So go ahead and open up your laptops and go to WebAssign.
I think this is the first time I used my laptop to calc.
Really? Yeah. All right. Oh, wait, I don't want that. I want that. I'm going to turn off the key. All right, so we worked bottom up in first period. We're going to kind of skip around today. So we're going to do number 1 first. So we're starting with radioactive decay. So just so you know, when something is growing, it means your K is going to end up being positive, and when something is decaying, it means your K is going to end up being negative. So here we're going to do radioactive decay. So a sample of a radioactive substance decayed to whatever percent you have there of its original amount after a year. Round your answers to 2 decimal places. What is the half-life of the substance, and how long would it take a sample to decay to 55% of its original amount? Half-life is the amount of time it takes for half of the substance to decay, so that you're left with half of what you started with. So half-life is a time value in years. All right, so here's what we always start with. So let's see, what do we want to use to represent radioactive substance? Pick a letter. You can just call it Y, or you can call it R for radioactive, or S for substance. I don't care. R? Okay. R equals CE to the KT. So no matter what, you're always going to start with CE to the KT, well, with the exception of Newton's law of cooling, which we'll get to in a minute. Okay. So we start with R equals CE to the KT. Now, C is your initial amount. They didn't give us any amounts in this problem. They gave us percentages of amounts. So here's the thing. We know that after 1 year, so T equals 1, the substance decayed to 94.5% of its original amount. If the original amount is C, how much would this be? It would be 0.945 C, right? Okay, so we get 0.945 C. So whatever your percent is, put that there, right? So percent of C equals CE to the 1K. Because my time is after 1 year. How are we doing? Is that okay? Charles, you good? Yeah? Okay. All right. Tyler, you good? Okay. All right. So now what happens? C's are gone, right? Goodbye, C's. Okay, so we have 0.945 equals e to the k. I need to find k. How am I going to solve this? Natural log both sides, right? So I end up with ln of 0.945. What's the ln of e to the k? Do you guys know ln of e to the k is k? Yeah. Do you all know that? It's real important. So just in case you don't know, ln of e to the k, what can you do with the k? Put it in front, right? And what's the natural log of e? 1, right? So ln of e to the k, ln of e to the stuff is the stuff, right? Okay. So our k is now ln of 0.945. Once you find that, put it back into your, rewrite your formula and get a new model. So now my model is r equals c e to the ln of 0.945 times t. We want to know the half-life. We want to know how long it takes for us to have half of what we started with. If we started with C, what are we ending with now? Half of C, right? So the information in the problem is so that you can kind of set up your model, and then you go to the actual first question and you say, all right, so I want to end with half of C, so half C equals CE to the ln 0.945 t. What can we do with the C's? Cancel the C's. Goodbye, C's. All right, so now I have 1/2 equals e to the ln of 0.945 times t. By the way, e to the ln of 0.945 times t is not 0.945 times t. So be very careful because it's not that, it's that, which is something different. So be careful with your simplifying. We had a lot of simplifying errors during the first period. All right, so instead, Now there is a way to simplify this if you really wanted to. You could think of it as, I don't want to do it. I'm not going to do it. We're just going to walk through and solve it. It's just, I tried showing how to simplify during first, and it was so many steps and so many people got confused that we're not going to go there. We're just going to solve this the way that we would. So whenever you have an E equation, what do you do to both sides? ln. So we have ln of a half equals ln of 0.945 times t. How do I solve for t? Just divide, right? So it's just ln of a half divided by ln of 0.945. So in your calculators, go ahead and do that for whatever your percent was. If anyone needs, does anyone need to borrow a calculator? You can use that brick. There you go. All right, so I got let's see, yeah, I got 12 point, carry this 25. Is that around what you guys got for whatever you were doing? What did you get?
I got 22.
You got 22?
Yeah, 15 points.
Okay, so they're not far off. It's just different percents. What was your percent?
97.
Okay, all right. So yours would go slower, so it would make sense it would take longer. You want to enter with 2 decimals, so 12. I'm going to put 12.25 for mine. You guys can put whatever you got for yours. Okay. How long would it take the sample to decay to 55% of its original amount? So instead of putting in 1/2 C here, what would we put in? 0.55 C. And then you're going to do the exact same thing. So see if you can do the exact same. Now yours might be different, right? Mine's 55, but yours might be 50 or 45 or whatever it is. Call me over if you need help. Oh, okay. Let's go back, go home, and go again. Okay, it's this, it's 3/8. Yeah. Guys, just, there are separate homework assignments with all those little names like radioactive decay homework or problems and population growth problems. Those are the problems that Ms. Grumald is using with her blended learning lesson today that I went ahead and linked if you wanted to use them for practice, but we're not going to be using them today.
Are they due tomorrow?
No, none of this. The only thing that's due is section 3A, and I always give you 2 class days, which means this homework is not due until next week, Tuesday. Yeah, but hopefully we'll get it done today. Did everyone get number 1 done? We good? Okay. All right. Except for Clementine, did you get it up and running? Oh, you can't use my numbers because your numbers are different. You did, this is you have 92.5 instead of 94.5, but we can do yours in 2 seconds, right? It's just ln of a half. So just bring this down, and instead of 0.945, you just do 0.925. Okay, so that's your first answer. And then your second answer, we want 55%, so instead of ln of a half, you do ln of 0.55. And there's your second answer. Because instead of 50%, it's 55%. Okay. Good. All right. Are we ready to move on? All right. We're going to do the big one next. We're going to number 4. It looks so innocent. Okay. We're going to walk through it together. All right. So stay with me. Don't work ahead unless you're like really, really confident. Okay. All right. Here we go. So is everyone ready? All good? Okay. A bacteria culture grows with a constant relative growth rate. After 2 hours, there are 400 bacteria, and after 8 hours, there are 50,000 bacteria. So I'm going to kind of write these as ordered pairs for a moment. So when t equals 2, there are 400, and when t equals 8, there are 50,000. For you, these numbers would be different. So write down your 2 bacteria population values. Okay? All right. So I'm going to call our function, we have to call it p because they're calling it p. So we're going to say p equals ce to the kt. Did they give us an initial number? No. When they don't give you an initial number, you're going to have to do a little bit more work to solve for an initial number. So what we're going to do is we're going to plug in our 2 ordered pairs. Remember, this is t, this is p. So first thing I'm going to do is put 400 equals ce to the 2k. So I'm plugging in my first ordered pair. Now I'm going to plug in the second ordered pair. 50,000, whoops, 1 more 0. 50,000 equals ce to the 8k. All right. We all together? Okay. We have a system of equations. 2 equations, 2 unknowns, c and k. So how do...
Please pardon this announcement. All juniors who need to retake their picture and all juniors who have not taken a school picture before, please report to the small gym. Again, juniors who need to take a school picture or retake a school picture, please report to the small gym.
Okay. Okay, go do that. We'll see you in a little bit. Smile big. All right. So, whenever you're in this class and you have a system of equations, usually the easiest way to solve is with substitution. So I'm solving for c in my first equation, and then I'm going to plug that in for c in the second equation. So I get 50,000 equals 400 over e to the 2k times e to the 8k. All right. What's e to the 8k over e to the 2k? E to the 6k, right? So I get 50,000 equals 400 e to the 6k. What do I have to do next? Divide by 400. Don't start ln'ing just because you see an e somewhere. You got to have the e by itself before you can natural log everything. So you got to divide the 400 first. So I'm going to kill off a couple zeros. 500 divided by 4 is 125. So I get 125, but you have to do your own numbers for whatever you get. All right. So now I ln both sides. And my k becomes 1/6 ln 125. Your k will be 1/6 ln, but it'll be a different number here, unless you have the same numbers as me. All of that, And we haven't even started the problem yet. All of that was just to find k for our model. Now we need to find c. So c, if you look at this red equation right here, c is 400 over e to the 2k. So this k is going to go right in there. Now we're going to do this slow because this simplifies really nicely, but it takes some good, clean writing here. So I'm going to write in a different color. All right, so c equals 400 over e to the 2 times 1/6 ln 125. If you want to put this in your calculator just like this, you can. That's absolutely fine. If you want to clean it up first, you can do that too. I'm going to clean it up just to show you how it cleans up, but if you want to just type yours, you'll get an integer. They wrote these problems so they all work out to integers. But this is equal to 400 over e to the 1/3 ln 125, which is 400 over e to the ln of 125 to the 1/3 power. E to the ln of 125 to the 1/3 is 125 to the 1/3. The e and the ln cancel. And this is the same thing as the cube root of 125. The cube root of 125 is 5. So my answer is 400 over 5, which is 80. So that was mine. Yours, you could honestly just put this whole thing in your calculator and get what the number is. But it should be an integer. Did everyone get an integer? Some nice, decent number. All right. I need to know that we're ready to do part B. Okay, everyone give me a thumbs up if you've got part A done. Yes, yes, yes? Yeah? Okay, good. All right, part B. So now we have to write a general population expression. Remember, our population is C e to the kt. Don't put in this big ugly thing for C. Just C is 80 or whatever number you got, right? So for me, I'm putting in 80 e to the, but I am going to use my correct k, to the 1/6 ln 125 times t. So whatever your k is, whatever your c is and whatever your k is, you need to put those in. How are we doing? Okay. Once you have parts A and B typed in, look up so I know you're ready. Okay, good. No. Okay, still got a few. Gavin, are you ready or no? Yeah, you're ready? Okay. Vishal, you ready? Okay. All right, good. All right, okay, so now we're going to find the number of cells after 3 hours. All you're doing is plugging in whatever number is here in for t. So, and then it says to round to the nearest integer, so you put that in your calculator and round it. Be careful how you enter it in your calculator, because this is a little messy. Let's see. Okay. I'm just going to check and see if your numbers might be the same. No, your numbers are different. No. Okay. right, so for me, I got 894. I don't know what you guys have gotten. All right. Are we all okay? Can't tell. Okay. Okay. All right. P prime. This is where we use the other formula that I mentioned, which is dp dt equals kp. That's another way of saying p prime equals kp. So p prime of 3 is just equal to k times p of 3. So whatever you got for part C, you just times it by your k. This is my k. Right? So whatever you got for part C, you multiply times k, and oops, that's this k, and that goes in there. By the way, I need to make sure I emphasize never round in the middle of a problem ever. Like you can round when you're writing the answers in the blank, but on your calculator, you should always be using the full numbers to go from step to step to step. We had a lot of students who thought that everything was good, and then when they entered in their numbers, they were wrong by rounding errors. So make sure that, especially K, you never round K. Ever, ever, ever. Always keep K exact. If it's 1/6 ln 125, you enter 1/6 ln 125. All right, how are we doing? We're good? Okay, in the back there, guys, we're good? Good, okay. Last part of the biggest problem of the day. When will the population reach, whoa, woo! When will the population reach for, I think they're for all of us, it's 200,000. Okay, so when will the population reach 200,000? So this is my population formula right here. So I need to say 200,000 equals, and then you put your population formula. In my case, it's 80e to the 1/6 ln 125 times t. In order to solve this, what are we going to have to, what would I have to do first? Divide by 80. So I would do, so I get 2,500. What would we do next? Take the ln of both sides. Whenever you have an equation with an e, you ln both sides. ln of 2,500 equals 1/6 ln 125 times t. And then to solve for t, all you have to do is divide. This one they want 1 decimal place. My answer is 9.7. All right, once you got it, submit. You see all those little green check marks. Oops. Okay. So here, wait, let me grab my glasses and I'll look at your calculator. So we did 894. The problem is you're using 894, but it's not 894. It's 894.427.
So just put in.
You gotta, yeah. So you need to put, yeah. Whenever you have 894 in there, you gotta use the full number. So, and this is what'll get you guys is like here, my P of 3 was 894, but it wasn't really 894. That was rounded, right? But when I do this next part and I do K times this, I gotta do K times the unrounded answer. Otherwise, I'm gonna be off. Good. Anyone else have some like red X's that they need help with? Good. We got through it and it really wasn't that bad. All right. Look, there's like practically nothing written, right? It's like nothing.
Well, I would take a whiteboard or two.
All right, I'm going to erase this. Are we good to go?
Yeah.
All right. Bye. Goodbye. All right. We are doing great on time. That's because we didn't do any examples. We're just doing homework together. Okay, we're going to do number 3 next because number 3 follows the same thing we've been doing. So number 3 is continuously compounded interest, which again follows the CE to the KT model. How long will it take an investment to double? If the value, if the interest rate in my problem is 4% compounded continuously, your answer, yours might have a different percent. Okay. Okay. So, I'm just going to call it like A for amount. So A equals CE to the KT. They gave us no numbers. When they give you no numbers, you have 2 options. You can pick your own numbers, or you can do it with using the letters that are there. I have an old habit of doing it using the letters, but I don't mind if we want to use the numbers. You get the exact same answer either way. So if you choose your own numbers, I will tell you the easiest value for C to use for your starting amount is 1, right? Because then, how long will it take to double? What do you want to end with? If you start with 1, you end with 2, right? So if you use your own numbers, you can just start with 1 and end with 2. I'm going to show you how to do it keeping the variables, and it's really no harder. It's and I think it's a slightly higher level mathematically. So anyway, so for us, we're not starting with 1, we're starting with C. C is our starting amount. So if we start with C and we want to double, what are we going to end with? 2C. So we end with 2C equals CE to the KT. When you do that, what happens to the C's? They cancel, and look at that. We're left with exactly what we would have had if we had just picked 1 and 2 for our amounts. Okay, so how do we solve this? Oh, wait, first we need, I didn't put in my K. So K, what does K represent again? K is your growth rate, right? In this case, since we are growing at a rate of 4%, what is K? 0.04. We always enter it as a decimal. So we have 2 equals e to the 0.04 t. We need to solve it for t. So you guys would have 2 equals e to the whatever your interest rate is here times t, and then solve it for t. What's the first thing we're going to do? ln both sides. That's what I got. Okay, so I'm writing 17.33, but just so you know, my calculator, if I have to use this number again, which I will, my calculator doesn't say 17.33, it says 17.3286795514. So that's what I'm going to use going forward. Okay, this next part, the equivalent annual interest rate, what that really means is if it wasn't compounded continuously, say instead it was just compounded with simple annual interest. Once a year, at the end of the year, they put the interest into your account, right? So when we are compounding continuously, we follow the CE to the KT model. When you're compounding n times per year, and you don't have to know this, but when you're compounding n times per year, it's your starting amount times 1 plus your interest rate divided by n raised to the nt power. Does that ring a bell? Okay. So anyway, we are going to, since we're compounding annually, our n's just going to be 1. So we have c times 1 plus r to the t. This is the formula that we're going to use to solve part B. So we're just going to do simple annual interest. Now, what are they asking us to solve for? The R, the rate, right? So that we can't use the 0.04 because they don't want us to. They actually want us to find R. So here's what we're going to plug in. So I'm going to erase this stuff. So I have space. All right, so we're using this formula now. So we started with C, we doubled, so we have 2C equals C times 1 plus R to the, and then our time is if we put our money in for this amount of time, what rate would we essentially have earned? So it's whatever time you got in part A. Be careful because when you put it in your calculator, don't round it. Put in the whole decimal. All right, what happens to the C's? They cancel. So you have 2 equals 1 plus R to the whatever time you got from part A. How do we solve this? There were some interesting suggestions in first period. That's what I would do. Yeah. Very good. So personally, whenever I have any kind of a funky problem with exponents, I tend to ln both sides. It just makes life a little bit easier. Some people are saying take the 17.3 third root of both sides. That works, right? But I am an ln kind of a person. That's my go-to. So I would ln this. So coming down here, ln2, 3, ln1 plus r. And then divide. So my way, which may seem longer, and you don't have to do it, but this is how I would have done it. Now I get to here. How do I get rid of the ln? When we have an E equation, we take the ln of both sides. When we have an ln equation, we E both sides. What we actually, the mathematical term for that is exponentiate both sides. What that means is you're going to make each side be an exponent of E. So what you get is E to the ln2 over 17.33 equals, what's E to?
All seniors who need to take a school picture or need picture retake, please report to the small gym. Again, all seniors, please report to the small gym if you need to take a school photo.
Okay, so E to the ln of 1 plus r is just 1 plus r. E and ln r's cancel each other out. So 1 plus r. So my r is E to the ln2 over 17.33 minus 1. Now they want this written as a percent, so I can tell you because I remember from my last period, I got R of around 0.0408. So I had to enter it as 4.08. They want it as a percent rounded to 2 decimal places. They mean two decimals after you've written it as a percent. All right, so give this a try. See how you do with your own numbers. If you took the 17.333, I can't even say it, root of both sides, it's much faster. It's just, for some reason, that's not what my head goes to. All right, once you get your numbers, enter them in, and let's see if we get some green check marks. Are you going to work these at home? That's fine. Good. All right, does anyone need another minute? Oops. No, because that uses your rate of 6%. And go above here is your trying to get one rate, so you can't use the 6%. Do you have a plug in? Oh, you can just, oh wait, you're talking about how you actually found the time.
Yeah.
Did you find it as L2 or 0.06?
Yeah.
But here you did L2 times 0.06.
There's like freshman sign of
Okay,
class to put,
so here, let's see.
I have that man.
But then wouldn't it be divided by L2? But this is still has an L2 at the bottom. Those are the level of rate geometry dash. So you got L2 times 0.06 times L2. It's not L2 times 0.06 divided by, so it's really just 0.06. So I would try that. All right. All right.
Hold on while it shook. It's bad.
Yes. Good. All right. Fantastic. Last one. We're going to have time left over. We could have done some examples. Maybe we're just moving faster because, I don't know, there's less. There were like 25 people in first period. There was a lot more slowing down. Okay, so the last one is the only one that doesn't follow the CE to the KT model. The last one is Newton's law of cooling. And I'm going to go ahead and hand out the handouts. All these are the Smartboard notes, just where I just took screenshots of the Smartboard notes and put them on paper because I thought we were going to work through all these and I didn't want to have you guys have to take time to write everything down. So I just took screenshots and printed them, so I might as well use them. So there you go. Okay, so Newton's law of cooling is actually on the back. So what Newton's law of cooling says, so in normal, regular population growth, we get dp dt equals kp. The rate of change in the population is proportional to the amount of the population at any given time. With Newton's law of cooling, it's dt, where big T means temperature, is equal to K times temperature of the object minus, they're calling it T sub S. T sub S stands for the temperature of the surrounding medium. So what does that mean? It means like if I bake a pie, and say the pie is 350 degrees when I take it out of the oven, and say my kitchen is 70 degrees, then the temperature of the pie, this big T is the temperature of the pie, T sub S is 70. T sub S, your surrounding medium, that's considered a constant. Technically, the surrounding medium acts on the pie. The pie doesn't really act on the surrounding medium. It's not like, if I take my 350 degree pie and I walk outside, people aren't going to go, whew, it's hot out here, right? It's just, it affects it a tiny bit, but not enough to really matter. So this guy is considered a constant. This is actually what we're looking for. So anyway, so when we have all of that, that being said, when you solve this, you end up with CE to the KT plus T sub S. So because of that, when you're doing Newton's law of cooling problems, your C no longer represents the starting value. Because at time 0, you don't just have C. You have C plus the temperature of the surrounding medium. So because of that, when you're doing Newton's law of cooling, and I'm going to rewrite this where I have a little more space. When you're doing Newton's law of cooling, you have to remember that C is no longer your starting value. So we have T of T equals CE to the KT plus T sub S. Okay. All right, so let's read this one. Now, by the way, Newton's law of cooling also works the other way. Like, you could also call it Newton's law of heating, because in this case, it's not something that's hot going into a colder environment, it's something that's cold going into a warmer environment. So the same relationship works to bring things up to temperature. So when a cold drink is taken from a refrigerator, its temperature is 5 degrees Celsius. After 25 minutes in a 20 degrees Celsius room, its temperature has increased to 10 degrees Celsius. Round your answers to 2 decimal places. What is the temperature after 30 minutes? So the good news is we all have the exact same numbers to set up for our model. So when a cold drink is taken from the refrigerator, so we're going to call that time 0. Our temperature is 5. So when T equals 0, our initial temperature is 5. So you plug in a 5 for your temperature, and you say CE to the 0 plus, and we need the surrounding medium. So after 25 minutes in a 20 degrees Celsius room, what's the temperature of the surrounding medium? What's the temperature of the room? 20. So this right here, that's our T sub S, the temperature of the room. All right. So e to the 0 is just 1. So what is C?
-15.
Thank you. Subtract the 20. All right. So now we have the model T equals -15 e to the k little t plus 20. All right. So that's based on our first point. We still don't know our k, our rate. So after 25 minutes, the temperature is 10 degrees. So now we can plug in a 10 for our temperature and a 25 for our time. What would you do to solve this first? Subtract the 20. So I'm going to come down here. Now what? Divide by negative 15. So you get 2/3 plus e to the 25. Okay. Now what? ln. And finally, you get k is 1/25 ln of 2/3. So our final model that we're going to use for all of our problems is big T equals negative 15 e to the 1/25 ln of 2/3 times little t plus 20. So there's your model. What is the temperature of the drink after? And then insert time here, right? So that's your first question. And then when will the temperature be 13? So that one, you're inserting a temperature in for your big T. Solving for little t. So go ahead and do those two problems. I'm going to pause the video. All right, so for those of you who were watching this on the recording, hopefully you could plug in the 30 without too much problem. I'm going to do part B real quick. And I'm just going to say, suppose our temperature is 13 equals negative 15e to the 1/25 ln 2/3 times t plus 20. First thing we do is subtract the 20, so I get negative 7. And then divide by 15, so I get 7/15. Thirds times t. Then I ln both sides. 15 equals 1/25 ln of 2/3 times t. And then to solve for t, you literally just divide the ln 7/15 by that whole thing, and you get a time. All right. Okay. And that's it. So I'm going to turn off the recording. Have a good weekend, everyone, if you're watching.